Hello everyone. In the previous lecture we had started with our derivation of the classical plate theory equations and we had reached this stage. Uh, in this lecture we are going to continue from exactly this place. Uh, the steps that we are going to do in this lecture, when I do this in a real face-to-face classroom on a chalkboard, even there it is fairly challenging because although the steps themselves are not that difficult, they are quite long. Now, I have never done this on a writing app before, so it is going to be a bit of a challenge to me also, but I'll try my best to keep things under control. Okay, so with that brief preamble, let us try to get to the business end of things. What I'll do is I'll copy paste this line and start off with the steps in the next page. All right. The first thing that I'm going to do is to transpose this negative sign to this left hand side, making all the terms positive. All right. Next, what I'm going to do is to play a little algebra or a calculus kind of manipulation, wherein I'll rewrite each of these terms in a certain fashion. So let me show that to you instead of describing it. I'll try to write it a little bit small so that things can be kept under control within the limited space that I have here. So you see what I just did. The term which was mx del square w del x square, I have rewritten it in this fashion, meaning that I have actually artificially incorporated an extra term like del mx del x times del w del x, because if you break it up you will get this term, but you'll also get that extra term. But I don't want that because I want there to be an equality between this step and the previous step, so I have to subtract this out. Let me write that as a separate integration. All right. Next, for this term, I'll do exactly the same thing. So you see the steps are a bit repetitive, but because there are so many terms, we have to be a little bit careful in keeping track of what term is going where. But they are not that difficult uh, in themselves. All right. For this last term, what I'm going to do, you see, I have two options in my hand. I can either select this del del x to operate in the way that I have done here, or I can choose the del del y to operate in the way that I have done here. But I also have this twice. So there are two terms involved here. So what I'll do is I'll choose one of them and use the del del x route, and I'll choose the other term and choose the del del y route. And you will see eventually the benefit of proceeding in that fashion. So first of all, going down the del del x route. So what is left inside is this del w del y, and then I compensate for the extra term incurred by subtracting out this term. All right. Next, I go down the del del y route for the other term. So this time within the bracket, I will have del w del x. Correspondingly, I have to subtract out this term with the partial derivative with respect to y. All right. So you see, it is not that difficult to understand. It's just long. Okay. Now is the part where we will actually use something rather clever and something which is fairly advanced as far as engineering mathematics is concerned. Okay, so this is sometimes referred to as the Green's theorem, and it has a direct connection with something which you are already familiar with, called the Gauss divergence theorem. That is something which we have been using all throughout our course on applied elasticity, and we have also been using it previously in this lecture, in this course itself. So what we say here is that so a brief interlude. A brief interlude regarding Green's theorem. Now, if you just search on Wikipedia about Green's theorem, I'm sure you will get sort of version which may not exactly look the way that I am presenting it here. But if you just apply your head a little bit and try to see the correspondence, you will see that they are basically the same. Okay, so what we are going to say is this: that suppose I have an integration over an area which is in this fashion: del p del x, okay, plus del q del y, where each of these p and q are themselves functions of x and y. So this is an integration with respect to the entire domain, to the entire area. So this area integration will be equal to an integration over the periphery of this area, or over the contour of this area, and where the integrand, it changes like this, where please note that this nx and this ny are the x component and the y component of the unit outward normal to the contour. So let me draw that diagram so it will be a little bit clearer. So suppose we are looking at this kind of an area. So in just the next slide, what I'm going to do is, of course, consider this general area to be this area that is occupied by our plate. So we'll be able to use the Green's theorem in this step, but just look at the theorem right now. So this is our entire area A, and this boundary here, that is the S. S is the boundary, A is the area. Okay, and what I'm saying here is that the unit outward normal at any generic point, that is given by this n hat, and the x component of that is nx, and the y component of that is ny. All right, so this Green's theorem basically gives us a method of going from an area integration to a line integration. So you see that this integration is only over this periphery, is over this contour. So this is basically a line integration or a line integral. So just like when we're using the Gauss divergence theorem, it gives us a method of going from a volume integral to an area integral. In the similar fashion, this Green's theorem, it gives us a method of going from the area integration to the line integration. All right. You can also reinterpret this term here as the gradient of some vector, uh, let's say some r vector, okay, where this r vector is equal to t I hat plus q j hat, okay. And because this gradient, of course this is the two-dimensional gradient, this gradient is the del del x I hat plus del del y j hat. So this gradient is like that. So if you take the divergence of this r vector, so del dot r or the grad dot r, you are going to end up with this thing here. And on the right hand side, what we have written is basically r dot n. Okay, so you can understand that this is what we are basically writing. And written in this fashion, it is somewhat reminiscent of what we had done back in our Gauss divergence theorem. It's reminiscent, it's not exactly the same, because there we were going from the volume integral to the area integral, and here we are going from the area integral to the line integral. Okay, now is the point where we are going to utilize this thing, and you see how we are going to utilize it. First of all, we have this term here. So if you just forget about whatever is inside here and you just think of it like this, del del x of something here, and then you consider this term where you have a del del y of another thing here. And then if you consider this term together with this term, then perhaps that would be a good way of proceeding with the application of the Green's theorem. Okay, because we can take this area integration together with this area integration, club these two terms together, and then rewrite those terms in the next step in the form of this line integration. In a similar fashion, uh, we can we can proceed with uh, we can proceed with uh, maybe this term and this term, all right, and then reduce that also. Okay, so let's see how much we can simplify, what terms we are left with, and what further steps we can take. All right, so what I'll do is I will again copy paste this entire thing. You see why it is a bit challenging to write this in this writing app. In a chalkboard, I would have fairly good amount of real estate to make these things visually more comfortable. Okay, but we'll have to make the best use of whatever we have and then proceed. So what we have here is this minus LHS bending. All right, so uh, I am going to consider first of all this term together with this term. And then by the application of the Green's theorem, let me just check if I think I've missed a delta here. Let me just check. So earlier I did have a delta over here. I had a delta and a delta. So I did miss that. So there was a little bit of a mistake at the end of the previous video, but no matter, we'll correct it here. So we'll have to correct it here also. and I'll have to correct it here also. I think uh, it'll be easier if I just select this delta W and copy paste it wherever necessary. So sorry about testing your patience like this, but this is something that needs to be corrected. And finally, for this term also, all right, I think I'm done there. So I think I'll have to copy paste this term now. Instead of this, uh, I'll go back and copy paste this. Okay, that should do it. All right, so I'm going to consider this term and this term. So this is mx del delta w dx nx plus my del delta w del y ny, and now this integration becomes a line integration that is over the entire boundary of our plate. Next, I'm going to consider this term together with this term, and what I'm going to obtain is mxy from here in this delta w del y nx plus this term mxy del delta w del x and y, and this also gets converted to a line integration, and the terms that I'm left with are these, this one, this one, this one here, and this one here. Okay, so let me just write those out. Now, as you can anticipate, what we are going to do here is uh, is basically to consider these terms in again the same fashion that we have been using the Green's theorem earlier. Okay, so the idea here is to ultimately go to a term which will involve the delta W only without any of these derivatives. So in this sense, what we are doing here is basically corresponding to what we did back in beam theory uh, when we went ahead with the integration by parts. Because as a result of the integration by parts, what we ended up obtaining was some boundary terms and then some integration terms over the entire domain. So in exactly the same fashion, as you see that after the application of the Green's theorem, what we have actually ended up here, at least over these two terms, is that these are integrations, no doubt, but they are integrations only over the boundaries. Okay, so they are a special kind of integration. They are over the boundaries. So going ahead, our plan is to again use the Green's theorem such that we will be one step closer to obtaining terms which will involve the first variation of W, but they will be devoid of any such partial derivatives. Okay, so in order to reduce the steps, what I will do is I will skip one step, that the step that I was going to write here, I'll skip it and then directly apply the Green's theorem on this term, on this term, on this term, and on this term. So all the remaining terms that I have not yet written here, for those I'm going to apply the Green's theorem. Okay, so first of all, considering this term, so you see it already comes with a minus here. So in order to adjust the artificially introduced term, what I have to do is use this kind of a uh, compensating term, and that will be in the form of this. So the extra term that we have introduced here is this del square mx del x square, which is exactly what I have written here. So we have just taken care of this term. Next, we are going to consider this one. These are all area integrations because we have not yet used the Green's theorem. We are just rewriting the terms. So now I'm rewriting this term here. So again, it appears with a plus because I already have a minus here. And now the compensating terms. All right. For this term, this term, I'm going to write it now. So I'm done with this term also. For this term, I have these. There should be a dA over here. And then a compensating term. Like so. So we are done with this term also. And finally, for this term, All right. So as I had mentioned earlier, we do have to keep track of a lot of terms. But there is a little bit of a good news here in the sense that you see this term here and this term here, they are the same. So at least something is going to be reduced in the next step in the form of a twice. Regarding the rest of the terms, you see this is the point where we use the Green's theorem again. Okay, because in the next step, this first term here and this second term here, they are not going to change. So whatever we have already obtained in the form of line integrals, they are going to remain as it is. These terms, we wish to combine them, these terms involving the area integrations, we wish to combine them in a fashion such that they will be amenable for the use of the Green's theorem. Okay, now which way should we go? That is the question. Well, you see, we do have a few, couple of different options. For example, one could think that perhaps one could combine this with this, because all that we need is a term involving the del x of something and the del y of another thing. So we do have an option over there considering this and this. So let me just number the terms so it will be easier to keep track of. I'm not going to number these earlier terms, rather I'm going to number the terms on which I am going to apply the Green's theorem. So this is these are the terms here, and this. Okay, so please note that I do have other area integrations, this one, this one, this one, and this one, but I don't have any intention of applying the Green's theorem over there. Okay, they will just get combined. Now, as I was saying, I wish to combine these terms in such a fashion that they will be amenable for the application of Green's theorem. So, should I combine 1 and 2, that is certainly one route, or should I combine 1 and 3? So, the route that I'm going to choose is to combine this 1 and 2, and uh, correspondingly, I will just combine this 3 and 4. Okay, so for the application of Green's theorem, let me just state it clearly and unambiguously that I'm going to combine this term 1 with this term 2, and I'm going to combine term 3 with this term 4. Okay, the rest of the terms I'm going to keep as it is. All right. So what I'll do here in this step, I think it will be just easier if I copy this entire thing and go to the next slide. Okay, this is still minus LHS bending. These terms, these first two terms, that I'm going to keep as it is. Okay, so I might as well copy paste them. All right. Next, combining this 1 and 2, what I'm going to get is this del mx del x delta w nx plus del my del y from this term 2 delta w and y. This entire thing becomes a line integration. Next, combining the term 3 with term 4, uh, so we have to be a little bit careful here. You see this here, although it appears before this term, but this is a derivative with respect to y. Okay, so what we need to be careful here is to write this as ny. And this is derivative with respect to x. So I'm talking about this derivative here and this derivative, the one outside the first bracket. Okay, so that is again a line integration, and all the terms that we're left with, I'll club them together because all of them are area integrations and all of them have as their coefficients this delta w. Okay, so I'm done with this term now. Next, considering this one, and next I'll combine this and this. So this entire thing has as its coefficient delta w, and this integration remains an area integration. All right. Now, it seems to us that all the applications of the Green's theorem that we could have possibly done, we have done. We have reduced a number of terms to integrations over the, not over the domain, but over the periphery of the domain or the boundary of the domain. So these are going to eventually contribute to some kinds of boundary terms, and we'll see them. But for now, our interest will focus our interest or our attention uh, to uh, to perhaps seeing if it is possible to simplify these things. Okay, because you see the motivation for such a step. Okay, so as a precursor to the next step, let me just state the motivation. Back in beam theory, we certainly did not write any moment terms. The all the simplifications and all the steps that we did were involved directly the bending variable, which was w, and you see embedded within this mx, my and mxy, which have been defined using the sigma xx, sigma yy and sigma xy, we do have the presence of the strains to the stress strain relations, and further those strain expressions can be written in terms of the displacement variable. So there is some hope that these terms here can be converted somehow in terms of the displacement variables. Okay, so let's see how we can do that. So this will be, once with this doing such a thing will be taking us one step closer towards obtaining a governing differential equation in terms of the displacement variables, much in the same way that we were able to do back in our bending theory. All right, so what we are going to do is we'll stop with the process of uh, going further with these steps. We will come back here, but for now we are going to take up each of these mx, my, and mxy. All right. So first of all, for mx, we note that as we had written earlier, this was our definition, minus h by 2 to h by 2, sigma xx z dz. Now sigma xx, back in our first lecture on, or back in our previous lecture, we had already written it in terms of the epsilon xx and epsilon yy. You can refer that back. The expression was e by 1 minus nu square epsilon xx plus nu epsilon yy, and then we have the z dz. Now the epsilon xx and the epsilon yy we are going to replace in terms of the displacement variables, and let's see what simplification that affords us, or what expressions we end up with. So epsilon xx, it was del us del x minus z del square w del x square, and this new epsilon yy, this epsilon yy was del vs del y minus z del square w del y square, and I should not forget this Poisson's ratio because this nu is multiplied over this entire epsilon yy. Okay, and then I have this z dz. Now you see we have this integration over the symmetric domain minus h by 2 to h by 2, symmetric about z equal to 0. So all the terms which are odd in the variable z, they are going to vanish, which means that this del us del x, which by itself is independent of z, but that is multiplied by this z, so this is z to the power 1, which makes this term here multiplied with this z an odd function, odd over this domain of z equal to minus h by 2 to h by 2, odd about 0. So that term is going to vanish. Similarly, this term where this vs also is independent of z, so that just leaves this multiplied with z to the power 1, so that is also an odd function effectively, and that also vanishes. These terms, however, there is a z already present here, so that multiplied by this z will result in a z square, so that makes this term over here, even though this w is independent of z, this w is independent of z, but because of the presence of this z square over here and this z square over here, this term and this term, they are going to be even functions and they are going to not vanish. So what we are going to end up with is this thing. So it's, let me just rewrite that, taking the minus outside. In fact, I can take the z square common between these terms, so that I'll be left with this. So that ultimately I can in fact take this term out of the integration with respect to z. I can take this entire thing outside of the integration with respect to z. And what I'll be left with here is this integration with respect to z minus h by 2 to h by 2, and that thing is just going to give me so I'll just do it in the rough column here in order to save some space. So this is going to give me a z cube by 3, limits h by 2, lower limit h minus h by 2. So this is 1 by 3, so that is z cube. So this is h cube by 8 times 2. So that is eventually h cube by 12. So what I have here is eh cube by 12, 1 minus nu squared, and then whatever was present inside the bracket. All right. In exactly the same fashion, if we proceed with the my, whose definition was like this, we are eventually going to end up with a term which looks exactly the same as the mx, except for a little difference which you can almost expect, that it is, instead of the del squared w del x squared, first we have this thing, and then we have the Poisson's ratio multiplied by this thing. All right. Next, let us not forget the mxy, and that is going to be a slightly different term, but we'll take care of it. So this is sigma xy z dz, and sigma xy is twice g epsilon xy z dz. Now g is e divided by 2 into 1 plus nu. This we had learned back in our applied elasticity course. And epsilon xy, that is half del us del y plus del vs del x minus twice z del square w del x del y, and that is multiplied by z with respect to z. So you see, just like we had in the case of the mx, this term over here and this term over here, they are multiplied by the z, so they eventually contribute to odd functions. So so this integration from minus h by 2 to h by 2 makes their contributions to vanish, and ultimately, oh by the way, I think I missed a minus here, so bad mistake. It should come with a minus because I had a minus over here. Okay, in a similar fashion I will have a minus over here. Now coming back to this thing, so you see, what I'm going to get here is, so you see, this 2 it cancels with this 2, this 2 it cancels with this 2. All right, these two terms, they vanish, and ultimately what we are going to have is just again this kind of an integration, because this z multiplied with this z gives such a z square dz, and this term, note, del square w del x del y is just independent of z. Okay, so what we are going to end up with here uh, is this e divided by 1 plus nu del square w del x del y, and then integration z square dz, lower limit minus h by 2, upper limit h by 2. And that, of course, I've missed the minus sign again. So ultimately this is again going to give me this h cube by 12. So eventually I'm going to end up with this minus eh cube by 12 into 1 plus nu, and then this del square w del x del y. So this is the term. So this expression here, this expression over here, and this expression here, that I wish to substitute back in these terms, okay, only in these terms, to see what sort of simplification that it gives us. Okay, so Let me just quickly try to do that in the next slide. I'll just copy paste out this part. So this is one luxury that I certainly did not have back when using the chalkboard. So I lose some, I gain some. Okay, I wish to obtain the expression for this particular combination of this expression, uh, the version of this in terms of the W. So this is del square del x square. This is minus EH cube by 12 into 1 minus nu square, and then del square W del x square plus nu del square W del y square. Next, for this term, I have del square del y square again, but this time del square W del y square plus nu del square W del x square. And finally, for this, I have twice del square del x del y, and within bracket I'll have minus EH cube by 12 into 1 plus nu del square W del x del y. Okay, so if I just let me see if I can simplify this a little bit. So one thing is good here, that I have this EH cube by 12, this minus EH cube by 12 common, and I'll also take this 1 minus nu square common, only I have to compensate with a 1 minus nu in the numerator. Let's do this. So I'll take this minus EH cube by 12 into 1 minus nu square common, and this gives me a del 4W del x4. So I'm operating this on this. All right, I'm done with that. Next, for this, I have del 4W del y4 plus del 4W del y square del x square. And for this, I'm going to have, let me not forget this 1 minus nu, because I have taken this 1 minus nu square in the denominator common, but I only had a 1 plus nu. So I'm effectively multiplying a 1 minus nu here. To take that common, I'll have to compensate by a 1 minus nu in the numerator. So, so you see, this term here and this term here, that gives me a twice nu del 4W del x square del y square, and I have forgotten this 2 over here. I'll correct that. Okay, so you see there is a minus 2 nu del 4W del x square del y square here. So this term here, and this term here with the nu, they cancel, and eventually I am going to end up with a certain nice looking expression, which is this. Because I'll have this twice of del 4W del x square del y square still remaining, I'll have to write that. You see, it is a nice expression. It is a really nice expression because this term here, this is something quite familiar to us, especially from our course on applied elasticity. You recognize that this is the biharmonic term. Okay, so this is the biharmonic operator operating on W. Okay, so this can indeed be written in this fashion. Okay, so another thing is that this particular combination without the minus, this EHQ by 12 into 1 minus nu square, that particular combination is given a certain name. It is called the bending rigidity. I mean, it is so very important within studies of plate theory. Uh, that is given a special name here. So this D equal to EH cube by 12 into 1 minus nu square, that is referred to as the bending rigidity. All right, so if we just go back to this over here, you'll see that this term, it has gotten expressed in terms of that minus d delta 4 w. So there is a certain simplification possible here. And please note that in light of what I had mentioned earlier, uh, these terms are eventually what are going to lead to our governing differential equation, or contribute to our governing differential equation. And because they have now been expressed in terms of this bending rigidity and this operator W, you see that it is actually shaping up to a nice form. And the last and the final governing equation that we are going to end up with, they'll have a certain symmetry and niceness to it. But we are going to cover, or we are going to complete those steps in the next video. So on that note, I will end this fairly long video. Thank you very much.